In this lesson, we're going to revisit a concept that we talked about quite a while ago called the mean value theorem. And just as a reminder, what the mean value theorem basically means is that we can determine the slope of a secant line over a given interval. Let's say A to B, as you see in the diagram in front of you. And so we determine the slope of that secant line. And what the mean value theorem states is that we then can find a point within that interval in which the slope at that moment is equal to the slope of the secant line. The example that I frequently use is that if we took a trip and we did our average speed, and let's say our average speed was 55, then that means sometime in that trip our speed must have been 55 at instant. It doesn't mean that the entire time we were traveling at 55 miles an hour, but it does mean that at an instant, at one point in that trip, we had to be traveling 55 miles an hour. Could be long time, could be just for a second. But the point is that at some point, there is a spot in which you had the slope equal to the slope of the average or the secant line. Now, in order for the mean value theorem to work, the graph must be differentiable. It must be smooth. So in looking at the two examples you see here at the bottom of your screen with the hyperbola and the absolute value of sorts, it's obviously upside down and above here. But when you're looking at it, to think about, to describe it, that's probably the best way you picture V-shaped graphs, or it's two lines comprised. Either way, you can tell that both of these, in each case, if my interval from A to B went on each side of this gap, so if this was A here to the left and B to the right, then the mean value theorem would not work. If, however, that we instead chose A to be within a spot in which it was smooth or differentiable, then we would be okay. And so the mean value theorem would work. Similar to this graph here on the right-hand side with this V, upside down V here, if I chose A to be on each side of this point, we would have a failure on that, and the mean value theorem would not work. However, if I moved A or moved B to be not including that point, then we would be fine in terms of verifying the mean value theorem. Let's look at an example. In our example here, we have f of x equals the absolute value of x. So first I would encourage you to go ahead and graph that. My hope is that this is a pretty standard graph, y equals x being one that runs from first to third, and so the absolute value would just allow that to bounce up. So there's our absolute value of x graph. If I'm to ask over 1 to 5, and I'm to verify the mean value theorem, let me refresh your memory how that works. To verify the mean value theorem is, first of all, can it be verified? Is it differentiable between 1 and 5? And of course, the answer to that is yes. So if I wanted to verify that, the first thing I would have to do is find the slope of the secant. And so in our case here, that means I'm going to do 5 minus 1 on the bottom. That would be that. And f of 5 minus f of 1. And of course, with the line y equals x, it's the same thing. And so it equals 1. Yay. And then it's saying, all right, step 2. If I want to verify the mean value theorem, that means that I would actually find f prime of x. Of course, with the absolute value, we're basically looking at the positive in this sense. And so the derivative of that spot, well, it's as basic as it comes. It equals 1. That's it, because the derivative of x is 1. And so what we're saying then is now we would set the two equal to each other. F prime of x set equal to the secant, the slope of the secant. And find where that happens. And of course, it happens on all the points there. And so that would allow us to verify that. But again, this is really just saying yes or no, can we use the mean value theorem? And of course we can. How about from -3 to 5? And of course, the answer to that is no, because of the point here, or the jagged edge. Well, let's continue on in our discussion about mean value theorem. So let's verify, let's remind ourselves how to do that. F of x this time is equal to x squared minus 2x plus 7. We're going to verify the mean value theorem from 1 to 9. Again, it helps if we understand that from 1 to 9 that this is in fact differentiable. Now this is a parabola, so my hope for you is that you understand, well, a parabola, there's no jagged edges, it is continuous, there's no real breaks or anything that's going to make it undefined. So we can go right ahead and do that. So what we're going to do instead is, just as I did the previous steps here, the previous page, the first thing you're going to do is the slope of the secant. And so that means that I'm going to do f of 1 minus f of 9. Certainly you could have done 9 minus 1, doesn't matter. And on the denominator, you're going to do in the same order. So f of 1 would be, so what I have is 6 minus, and you plug 9 in, you get 70 over 1 minus 9. So I have negative 8 on the denominator, and 6 minus 70 is negative 64. And so we get a positive 8. Okay, step number 2, f prime of x. And so f prime of x would be 2x minus 2. Step 3, set f prime of x equal to the slope of the secant. And so I'm going to take 2x minus 2, I'm going to set that equal to 8. So you add the 2, and you divide by 2, and you get x equals 10. Sorry, 2x equals 10. Divide, you get x equals 5. And so that basically, you want to check. Does 5 fall within that interval? And of course it does. So check, it does in fact verify it. All right, now find the maximum value of y equals x e to the x over negative 3 to 0. Slightly different kind of question, no longer mean value theorem. And so just want to address this as our last example in this video. To find a maximum or a minimum, first thing I want you to understand is that you always, always, always want to check the interval. Always check the endpoints. So I am going to check negative 3, and I am going to check 0. That is a definite. And also, in addition to that, you know that our max and mins occur at our first derivative. We can figure out our max and mins when our first derivative equals 0, right? That's your horizontal points of tangency, or points of horizontal tangency, because that's where a maximum would occur or a minimum, and then it would curve to go the opposite direction. So I am going to have to find f prime of x. So there's a couple parts to this. So let's start with plugging in negative 3. This would be negative 3 e to the negative 3. So that's negative 3 over e cubed. If I plug 0 in there, you get 0. Awesome. Now let's do f prime. It's going to require the product rule. So first times the derivative of the second plus the second times the derivative of the first. And we're going to set that equal to 0. And if you recall, whenever you have e to the x, or anything for that matter, you want to pull out what's in common and see what you get. Well, e to the x will never equal 0, so that's pretty much a moot point, but we have x equals negative 1. So the other one I want to check is negative 1. And if I plug negative 1 in there, I get negative 1 over e to the negative 1, or negative 1 over e. So which is the maximum value? What's the highest this graph is going to go? And of course, as silly as that may seem, 0, 0 is the highest that this graph would go. All right, so that covers in this particular lesson the mean value theorem, showing you a couple applications graphically, as well as this one verifying of the mean value theorem. And then lastly, looking and reminding you of how to find the maximum value. And if I can tell you anything about that, caution you that people tend to mistake on, is they always forget this endpoint thing. So always check your endpoints. Check that negative 3, check the 0, and then find that derivative. Don't just automatically assume the derivative is the max or the min.